everyone, my name is Usha and I'm excited to present our project titled Microcontroller-Based Washing Machine Simulation using PicsimLab. First, I'm thankful for providing us with this 1 month valuable internship opportunity, which we developed as part of our embedded systems internship at Emertxe. This project was a collaborative effort by our amazing team members Swathi, Kavya, Mitesh, and myself, Usha. Together, we explored how embedded systems play a key role in automating real life appliances like washing machines. Now, let's dive into the details of our project. Let's explore how embedded systems help automate home appliances like washing machines. In today's busy world, automation saves time and energy, which means in this today's fast-paced world, washing machines reduce the manual effort and improve household efficiency. With embedded systems and microcontrollers, traditional machines have evolved into smart automated appliances. Modern washing machines are now intelligent, user friendly, and energy efficient. This project focuses on designing a smart washing machine system using the PIC16F8 77A microcontroller. Emphasis is placed on reliability, automation, and user adaptability to simulate real world washing machines. Washing machines have evolved using embedded systems to perform smart tasks automatically. Our project uses a microcontroller to simulate this functionality, virtually making it easy to test improve. Now let's understand what actually an embedded system is. A dedicated computer system designed to perform specific functions within a larger device is known as an embedded system. It combines both hardware and software to execute a predefined task. Embedded systems are unlike general purpose computers. It handles only one specific function efficiently, optimized for speed, reliability, and low power consumption. These embedded systems are commonly used in the devices like washing machines, the project which we are working out, and then even in microwaves, cars, and industrial machinery. It is a compact computer system built to do only one specific task. And then, to go more vibrantly about this project, we should look into the block diagram which shows how different parts of the washing machine system are connected. Input switches are used to select modes or start the machine. Timer and reset manage the operation timing and allow restarting. The microcontroller which we used in this project is PIC16F877A is the brain that controls everything. It connects to the output devices like the motor, buzzer, fan and water valve through ports. The display unit shows status or time remaining. All the components work together to simulate the washing machine process effectively. And this block diagram shows the key components of our system. And then the embedded systems come in different types depending on how they function. Some react instantly like airbags, while others work independently like micro ovens. And we also have mobile and network systems and highly integrated SoC based ones found in wearables and smartphones. If we look more deep into it, these are classified as real time embedded systems which respond to the inputs within a specific time limit, which are seen in airbag systems in cars and in medical devices, and followed by the standalone embedded systems which work independently without a host system, which can be seen in washing machines and microwave ovens. And then it is also seen in networked embedded systems which are connected to a network for data sharing, which can be seen in smart home devices and IoT Internet of Things thermostats. And in mobile embedded systems, these are the audible devices with embedded control, which are seen in smartphones and fitness trackers. And then these are also classified as embedded systems on SoC, which is the system on chip, where all the components are integrated on a single chip. These are used in smartwatches and even in digital cameras. Embedded systems are everywhere, from kitchens to hospitals. Based on their applications, in the real world, these are classified as following: consumer electronics. These are seen in TVs, washing machines, and even in cameras, which enable the automation and smart user control, and also seen in automotive systems, which are used in ABS, airbags, and even in GPS to enhance the safety, performance, and comfort. These are found in the devices in ECG machines, pacemakers to ensure the precise monitoring and treatment, and also in telecommunications, which are embedded in phones, routers, and base stations, which support the communication and signal processing, and also used in industrial automation, which are used in PLCs, CNC machines, and robotic arms, which improve the productivity and reduce the manual effort and improves the efficiency. They make the devices smarter and more efficient, whether it's a TV, a pacemaker, or an industrial robot. This shows how powerful and useful the embedded systems are in modern life. This project gave us hands on experience in simulating an embedded system for real life use. It helped us understand how microcontrollers automate everyday tasks. And the following slides of programming and tools used in our project will be followed by my friend Mitesh. Thank you.
Thank you, Usha. I am Mitesh, going to explain what are the languages, development tools, and the components used in this project. We use C and the embedded C programming languages. C is a general purpose, high level programming language known for its simplicity, efficiency, and close to hardware control. It is extensively used for developing system software, operating system, and low level programs because of its speed, portability, minimal runtime overhead. The only difference between the C and the embedded C is an extension of the C. Embedded C offers direct access to the hardware features like registers, input-output ports, and memory locations using specific syntax and hardware-specific keywords. Embedded C enables writing efficient and real-time coding for controlling hardware devices such as sensors, motors, LEDs, and other peripheral devices. Now let us see the purpose of the project. This project simulates a washing machine using PicsimLab and the PIC16F877M microcontroller, aiming to replicate real-world washing machine operations in a virtual environment. It begins with an understanding of the washing machine components and the operational parameters, including fabric type, load size, and water level. To accurately define laundry conditions, the system implements washing cycles using timers, motor control, and user interaction through switches and LEDs, showcasing automation and embedded control. Now let us see the development tools. The first comes MPLAB IDE. IDE stands for Integrated Development Environment, which is developed by the Microchip for programming Pixie and DS Pixie microcontrollers. It supports code writing, compiling, debugging, and simulation in one platform. It provides built-in support for MPLAB XE compilers and hardware tools like PicKit and ICD. It also offers real-time debugging, breakpoints, and watch windows for efficient troubleshooting. Compatible with Windows, Mac OS, and Linux, supports project management with version control. The other tool is XC8 compiler. It is designed for 8-bit PIC and AVR microcontrollers. It is fully integrated with MPLAB XID for seamless development. Generates optimized and efficient machine code for embedded systems. It also supports ANSI-C programming for better portability and readability. It offers multiple optimization levels. It includes free optimization level, standard pro optimization levels, and the pro optimization levels. It also includes libraries for peripherals like timers, analog to digital converters, and the GPIO. It is available on Windows, Mac OS, and Linux platforms. The third one comes PicsimLab. PicsimLab is a graphical simulation tool for Pixie microcontroller projects. It also allows users to test embedded systems without physical hardware. The main advantages of is to test embedded systems without physical hardware. Supports real-time simulation of circuits, LEDs, motors, switches, and more. Compatible with .hex files generated by MPLAB XC8. It provides a virtual lab environment for learning and the prototyping. It is also useful for testing embedded firmware, debugging, and verifying input-output logic. Now we discuss about the main component of this project, that is microcontroller PIC16F877A. It is a popular 8-bit microcontroller from the Microchip, known for its simplicity, reliability, and versatility in embedded systems. It has 40 pins, supports both digital and the analog input-output, and operates at speeds up to 20 MHz, making it suitable for real-time applications. It is equipped with 368 bytes of RAM and 8 KB of flash memory. It can handle only moderate complex programs efficiently. Offers built-in peripherals like ADC, stands for analog to digital conversion, universal asynchronous receiver and the transmitter, pulse width modulation (SPI), and timers, enabling a wide range of control and communication tasks. We can example of the timers is watchdog timer, commonly used in automation, robotics, and education, and is programmed using MPLAB X IDE with the XC8 compiler for easy development and the debugging, as we have discussed in the previous slides. Now we will see about the components used in this project. The first comes is tactile switches. In microcontrollers, switches are often used as an input to control the operation of the device or to interact with the user. When the button is pressed, the switch turns on, and when the button is raised, the switch turns off. An array of tactile switches form the digital keypads. Each switch has its own operation. We will see some of them. The RB3 is used as switch for navigation, scrolling between options. The RB4 is used as switch 5, powering on the washing machine and the resume. The RB5 is used as switch 6, stop and pause the ongoing program. The RB0 is used as a switch to indicate the status of the washing machine. To know about more components in this project, I would like to invite Kavya Sri to explain the input and output components and how the user interacts with the system.
Mitesh. Hi, I am Kavya. I am going to presenting about these topics. Digital keypad. A digital keypad is an input device consisting of multiple push buttons arranged typically in a matrix format. Example 4 by 4 or 3 by 3. It allows the user input numeric or control data into a system by pressing individual keys. The microcontroller scans the rows and columns of a keypad to detect which key is pressed by reading logic levels. Keypad are often used for user authentication, menu navigation, setting parameters in an embedded system. The keypad allows the user to select washing modes. It provides an efficient and interactive method for user input without requiring a graphical interference. Another one is CLCD. A character LCD is a display module capable of showing alphanumeric characters and symbols on a screen, typically in 16 into 2 or 20 into 4 formats. It is commonly used in embedded systems to present real-time information to users such as operation status, error messages, menu options. CLCD operates by sending control and data signals from the microcontroller to display via GPIO pins. It offers a clear and continuous visual representation of a mission operates for the user. Next one, timers. Timers are internal modules in microcontroller that count clock cycles and generate precise time delays or measure intervals. They can be configured in various modes such as delay generation, event counting, pulse width modulation, PWM. Timers operates independently from the main execution loop, allowing time-based operations to run in the background. Timers manage the duration of each watch cycle, stage, wash, rinse, spin by continuous specific time intervals to ensure accurate cycle timings and free up the processor of the other tasks. The another one is ISR. An ISR is a special function that automatically executed by the microcontroller in response to an interrupt event. Interrupts allows a system to pass in the current task and respond immediately to external or internal events like timers, overflow, or key presses. This mechanism enables real time responsiveness, especially in time critical applications. ISRs are used to handle events such as timers, compliances, or keypad input without delaying ongoing operations. They improve the responsiveness and multitasking capability of washing machines control systems. The another one is buzzer. A buzzer is an electronic audio signaling component that produces a beeping or buzzing sound when a voltage is applied across to it. It is commonly used in embedded systems to indicate events such as alarms, cycle completions, or user alerts. Buzzers are available in two types, one active and another one is passive, and are easily interfaced with microcontrollers using a digital output pin. They are widely used for providing immediate and audible feedback in the control system. The buzzer is activated by microcontroller to produce the sound to end of the cycle or during the fault conditions. It provides an audible indication to the user, enhancing to interactivity and responsiveness of the system. The another one is LED. An LED is a light emitting diode. It is a semiconductor device that emits the light when an electric current passes through it in a forward direction. It is one of the most common output indicators in the embedded system used for showing system status, process, or error alerts. LEDs are lower power, long lasting, and come in various colors, making them ideal for clear and direct visual communication. LEDs are controlled to turn on or off based on the current washing stage, such as wash, rinse, or spin. They provide a simple and efficient way of users to visually monitor the operation status of the machine. Another one is fan. A fan is an electromechanical device that produces airflow for cooling or drying purpose. In embedded systems, it is controlled using a transistor or relay connected to a microcontroller. It adds realism by simulating drying functions in an automated systems. The fan is turned on during or after the spin cycle to simulate an air drying process typically found in modern washing machines. It demonstrates the ability of a microcontroller to manage real world electromechanical device based on the program. Okay, now I will hand over to Swathi who will explain the functionality of our project and shares the conclusion.
Thank you, Kavya. Hi, I'm Swathi. I'm going to cover the topics about functioning of this project, project demo, and conclusion. Coming to the functioning of this project, this block diagram illustrates how Pixie 16 F877A microcontroller controls the operation of a washing machine simulation using PicsimLab. Inputs to the microcontroller are switch 5, power on, used to start the washing machine system. Switch 6, pause or stop, lets the user pause or stop the current operation. Switch 4, navigation, allows controlling through washing modes like wash, rinse, or spin. Switch 1, door status, detects if the door is opened or closed for safety control. Coming to the outputs from the microcontroller are CLCD display, crystal LCD, shows the current mission status like washing, rinsing, paused, or completed. Buzzer provides audible alerts for events like cycle completion or errors. Fan stimulates the drying process after the spin cycle, controlled automatically by the microcontroller during the final stage. Now let's move to the most interesting part of our project execution, the live demonstration of the project. The code for this project was developed using MPLAB IDE. It is organized into multiple modules for better structure. The different files that are included in source files are main.c, controls the overall flow of the project. ISR.c, timers.c manages the time delay for washing stages. Digital keypads.c handles keypad inputs. CLCD.c manages the LCD display. Program functioning.c contains logic for the washing modes and execution. And there are different header files included. Those are clcd.h, digitalkeypad.h, main.h, projectheader.h, timers.h. Each file plays a key role in building modular and maintainability embedded C code for the simulation. After the project is built successful in MPLAB IDE, we are going to load the code into the PicsimLab. Now let us see the execution of our project in PicsimLab. First of all, we need to load the hex file into the PicsimLab. After successful loading of the hex file into the PicsimLab, the CLCD displays a message, press switch 5 to power on washing machine. Pressing switch 5, it displays a message, powering on washing machine. After the washing machine powered on successfully, it displays the list of the washing programs such as daily, heavy, delicate, whites, stain wash, eco cotton, woolens, bed sheets, rinse plus dry, dry only, wash only, Equasto. In order to change the mode of the washing program, we need to make a short press of switch 4. To select the washing program mode, we need to perform long press of switch 4. Here I am selecting the daily washing program mode by making the long press of switch 4. After the washing program mode is been selected, it displays a message of water levels with auto, low, medium, high, max. To change the water level mode, we need to perform short press of switch 4. To select the water level, we need to perform the long press of the switch 4. Here I am selecting the low water level by performing the long press of switch 4. After the water level has been selected, now it displays a message, press switch 5 to start the execution, press switch 6 to stop the execution. In order to start the execution, we are pressing switch 5. It gives program daily and the time 33 seconds. Here the function is wash and the time is been reducing. Rotation of the fan indicates the running of the program, and it displays two messages in the LCD such as switch 5 to start, switch 6 to pause. In order to pause the execution, we are pressing switch 6. After pressing switch 6, the execution of the program has been paused and the timer has been stopped with the rotation of the fan has been stopped. To resume this operation, we are pressing switch 5. After pressing switch 5, the timer starts again decreasing down and the fan starts rotating again. To check whether the door is opened or not, for door open, we are pressing switch 1 by making it the long press. Here the message is given as door is open, please close the door with the buzzer sound. After resuming the switch 1, it performs its operation, and finally, after completion of the project, it gives program completed, remove the clothes with a beep sound. Now let us check with another washing program mode. Now I am selecting heavy washing program mode by making long press of switch 4. Now I am selecting the water level as a medium by making long press of switch 4. Here I am starting the program by pressing switch 5, heavy and with the time 45 seconds. It starts the timer decrement and fan rotating. For the door open, I am pressing switch 1. Door is open, please close the door with the beep sound. I am resuming the switch 1. The execution being continued from where it was stopped previously. Timer being decreased continuously. And the functioning of the program is being changed from wash to rinse and spin. After successful completion of the project, it gives a message, program completed, remove clothes with buzzer sound for few seconds. Conclusion of the project. The project successfully demonstrated the stimulation of fully functional washing machine using the PIXI-16F877A microcontroller on the PicsimLab. It performed valuable hands-on experience in embedded system design, including working with timers, interrupts, and digital I/O interfacing. The system efficiently automated common washing machine functions, showcasing how embedded technology can simplify real-world household tasks. A clear and interactive user interface was developed using components like LEDs, buzzers, keypads, and an LCD display for real-time feedback. Through this project, essential skills in embedded C programming, circuit design, and microcontroller-based system development were significantly strengthened. Thank you everyone for giving us this opportunity.